Hello, everyone, and welcome to my talk at the Informs Annual Meeting 2021. My name is Álvaro Lorca. I am an associate professor at Pontificia Universidad Católica de Chile, and this is joint work with Felipe Verástegui, Daniel Olivares, and Matias Negretti. And this work is called Optimization-Based Analysis of decarbonization pathways and flexibility requirements in highly renewable power systems. Okay, so we are talking, of course, about renewable power, basically variable renewable power, mostly wind power and solar power. In this case, photovoltaic solar power. We know that these two sources of energy are very variable throughout the day. They cannot be forecasted accurately, and they introduce significant levels of variability into modern power systems. Therefore, we need to correctly assess the needs for flexibility and proper market designs in power systems that include or integrate a significant amount of these types of energy sources. And these power systems throughout the world need to carefully analyze how to decarbonize their respective power systems in order to avoid security problems or significant issues with how their power systems work. Another important technology in this context is concentrated solar power, especially in countries with significant radiation levels, such as Chile or Spain, and many other countries with good radiation levels. And CSP is a key asset in decarbonization processes because even though it might be expensive for now, it includes significant flexibility and dispatchability, and is completely renewable. Other important technologies are batteries, of course, and really any kind of storage device, such as compressed air technologies, for example. Another significant question that we will not touch upon today, but which, which it could be a critical issue in the next few years and opportunity, is hydrogen. Okay, here we have a hydrogen-based car by Nikola. And hydrogen could be a way to include significant levels of flexibility into energy systems. Another significant issue in many countries is the context of water availability, okay, or droughts, and we're seeing significant more levels of drought in many parts of the world. So, okay, we want to, this is a coal generator. So we want to reduce emissions or decarbonize power systems. And at the same time, we want to add variability. So we need to carefully design these processes. Also, water might be a very, very important resource in many parts of the world because it's a very flexible power source. Okay, so here we have a large reservoir that can that needs several months of planning because there's a lot of water that can be stored in these types of reservoirs. So how do we understand the role of flexibility in highly renewable power systems? This is the type of question we ask in this talk. Okay, and in particular, we should always take into account the fact that many power systems have a high level of spatial complexity. We need to take into account transmission aspects in detail if we want to decarbonize power systems and correctly assess for flexibility needs throughout power networks. Okay, so in the next of this talk, I'll briefly introduce the problem we're studying. I'll go over our methodology, discuss a case study on the Chilean power system, and conclude. Okay, so a little bit more of introduction. The climate is undergoing through drastic changes. We all need to see the last IPCC report to see that climate change is occurring in a very fast way, and we're facing a significant threat if we don't act fast. Okay, so for example, in the case of Chile, the energy sector accounts for about 80% of the CO2 emissions. And thus, if the energy sector reduces emissions, then we can start addressing climate change in proper ways. Okay, and the electric sector is usually a small part within the energy sector, but in the next years and decades, we should see significant waves of electrification of energy that will allow us to decarbonize energy systems through decarbonizing electric power systems. So many questions, right? Is this too fast? Is this fast enough? How fast should we decarbonize? And from a climate change perspective, we need to, and a humanity perspective, we need to decarbonize as fast as we can. Okay, so this work provides an optimization-based analysis to assess decarbonization pathways and their impact over system flexibility requirements in modern, highly renewable power systems. Okay, so for example, in the case of Chile, coal produces 40% of energy generation today from the power sector. And thus, completely eliminating coal-based generation is a significant challenge. Okay, so how do we correctly account for flexibility, as I've mentioned before? Okay, so what do? We build a long-term capacity expansion planning model looking for a 20-year horizon. Okay, we will go over a case study for Chile, but all of our models and methodologies are really applicable for really any country or any power system. So in the particular case of Chile, and many, and this is only an example, many other countries have laid out particular decarbonization schedules where coal power plants are to be closed in given times. And in the case of Chile, there's already quite an ambitious program in the next 5 years or 4 years, and with more specific plans for closures in the next 2 decades, with every plant closed before 2040. And there's significant discussion on accelerating this schedule, maybe thinking about decarbonization in 2035 or even 2030, and things like this. Okay. So in this work, we will study different decarbonization goals with complete decarbonization by 2040, which we will call D40, by 2035, which we will call D35, and by 2030, which we will call D30. So we employ this mathematical representation of the power system, okay, through an optimization model that basically minimizes the total system cost, including both infrastructure additions or capacity expansions and employment or operation of those assets, okay, namely generation costs and so on. And this model minimizes the total costs, namely investment plus operational costs over the given horizon, a 20-year horizon in this case, while satisfying all of the demand and physical constraints of the power system. That's the overall idea. In this paper, in this work, we take 6 periods of 4 years each. Okay, so our horizon really goes up to 2044, and these last 4 weeks are just to avoid end of horizon effects. Okay, so there's significant works on capacity expansion planning models. This is out of the scope of this talk to go over an extensive literature review, but we may name here a few of the previous works that were key works that laid out many key concepts for our work. Okay, so in our Chilean case study, we consider a system representation with 20 zones or 20 buses in this case, and 20 transmission corridors. Okay. We also built quite a detailed hydro network, which we embed into the model because hydropower is very important in the case of Chile and many other countries. We represent the years through 6 representative days, which are selected based on clustering methods. And these days represent solar power, wind power, water availability, and power demand. We also study in this model the various different ways to represent flexibility constraints, and we employ particular linear relaxations of unit commitment aspects, which account for better models than others in terms of capturing the flexibility and operational dynamics of the power of a highly renewable power systems. Okay, and we employ a lot of different data for existing and candidate units for transmission lines, for generation units, and so on, cost projections for the future, and so on. You can check for details in the paper. And all of the models were built based on Python, employing Piomo, Gurobi as a solver, and starting from the so-called switched model. Okay. So our results on the case study on the Chilean power system. Okay, this is the main result. We have decarbonization by 2040, by 2035, and 2030, respectively. Total cost increases because as we move to the right, the system is more constrained because we need to eliminate coal-based generation earlier. Okay, and then, for example, we can see here that the investments are much higher in terms of generation if we need to decarbonize 10 years earlier than 2040, right? There's significant $5,000 million more if we need to decarbonize by 2030 than 2040. Transmission is not too different in the 3 cases. Fixed operation and maintenance costs increases. Variable operation and maintenance cost is not very sensitive. Fuel consumption decreases, okay, and carbon taxes decreases a little bit, right? Okay, so then what about the capacity mix? Here we can observe accelerated coal phase-out process in D35 and D30, and we see, if you look at the gray part here, it removes by 2040, by here, it's completely removed by 2030, okay? And is replaced by a photovoltaic, wind power, and also CSP and batteries, which are key for faster transitions or faster decarbonization processes. So namely, this shows how as you remove coal faster, you need to integrate CSP and batteries to add sufficient flexibility to accommodate for photovoltaics and wind. These are the investments throughout time. So both D30 and D35 require larger investments in earlier stages of the horizon, okay? With investment peaks right before complete removal. For all scenarios, investment in variable sources balanced with flexible gas, CSP, and battery systems. So this also shows that gas can be an alternative for adding flexibility to the power network. Of course, it still carries out an enormous amount of emissions. So future work will study if we can completely eliminate gas and what are the costs of doing this. And generation mix looks like this. It's amazing to see how CSP starts entering earlier if coal is removed earlier, of course. But in all cases, even in D40, CSP plays a significant role in the final power mix. Okay, so here is the generation mix change. So this is 2020 and 2040. The final generation mix is not too different, but the trajectories, as I showed, are different. Okay, so in the end, we have a significant amount of CSP of about 27% of the generation mix, and a small percentage of fossil-based generation, which is 7% gas. So this is how the 6 representative days look throughout the day. These are 24 hours for the 6 representative days in 2020. And these are the same 6 representative days, but in the case of 2040 for D40, where we see a significant role of CSP as a flexibility provider and an important role of gas units, which are modeled with the flexibility constraints mentioned before. So technologies such as gas, hydrodam, and batteries aid in supporting variability, and steady generation from CSP, as I mentioned, is observed. Okay, these are the thermal storage cycle in 2020 and in 2040 for the D40 case. So the thermal storage cycle further emphasizes the role of CSP, providing carbon-free baseload generation in 2040, being charged in sunny hours, of course, but providing power through the whole day. So this is CSP with a large number of storage, of hours of storage. And then CO2 emissions start driven mostly by coal and end up driven by gas, with significant reductions of overall CO2 emissions. Finally, I would like to mention that decarbonization is a key process under the current climate crisis to enable a low carbon economy. This process creates key flexibility challenges in power systems. The use of planning models may provide insight on operational issues to be expected and the role of new technologies in this transition, as this study shows. Okay, so this is our paper. This is published in Energy, and please check it out if you want to go ahead further into the details of our study. Okay, so finally, I would like to mention a few thoughts from all of this process, mention a few challenges and opportunities in terms of decarbonization and overall sustainability of energy systems. So first of all, real-time re-optimization of power network operations is very important in many countries such as Chile, where this is not currently done. So we need to operate power systems in real time in better ways. Markets for ancillary services and associated compensation schemes are key. Here we showed results from a centralized optimal capacity expansion planning model, but reality doesn't work like that. So we need correct signals to drive the system, or to drive the different agents to the right outcomes of the system. Also, we need to improve the use of hydroelectric resources in countries such as Chile, because water storage is an important flexibility provider. Okay, and there's an increasing risk management opportunity because of the threat of climate change. This raises the importance of correct risk management. And we need to correctly use intradaily storage capabilities. Okay, so for example, CSP, batteries, or even run-of-river hydro. Also compressed air energy storage, and other technologies that provide storage throughout the day. Adequacy, capacity values, and long-term actions need to be correctly implemented. Power system resilience is very important as a challenge as well, if we're removing coal and adding more variable renewable power. Smart grid concepts in distribution networks is also a very important way to accommodate more flexibility in power systems. And social and fairness aspects are also very, very important. If we're removing coal, this is a lot of jobs, and we need to correctly and properly transition and help those populations to get better jobs, hopefully in green energy. Some opportunities. Countries such as Chile and many other countries are becoming a leader in the use of solar power and could be leaders in the production of green hydrogen. Also, becoming a zero-emission country is a significant opportunity. Do we need to redesign our economic systems and societies? I would say yes, but this will require a lot of us to think out of the box. Also providing an important example for the rest of the world, for those countries that take the lead on this process of completely removing emissions. So look at this sentence from Immanuel Kant in 1797. There is only a single categorical imperative, and it is this: act only on that maxim through which you can at the same time will that it should become a universal law. So don't wait for other countries to decarbonize their energy systems. Go ahead and be the first. Some final thoughts: the importance of a solid interface between science and industry, the importance of well-designed markets with properly aligned incentives, the importance of re-asking fundamental questions when dealing with complex systems. Okay, so I would like to say that energy systems are evolving quickly, and we should not only try to adapt old solutions when trying to solve new problems. And we should really think not about what was before, but what should be in the next years. Finally, I would like to mention that you can check out our laboratory's website, the Energy and Complex Systems Laboratory, for more information on related research from our lab. This is the link. So that's my talk. Thank you so much, and we'll hopefully see you all soon.